History of probability. From games of chance to modern statistics. Introduction. Probability, the science of uncertainty and chance, has a rich history that has evolved over centuries. It is a fundamental concept in mathematics, statistics, and a wide range of disciplines. In this video, we will delve into the captivating journey of probability theory, from its early origins in ancient civilizations to its modern applications in fields as diverse as science, technology, and finance. The history of probability is a testament to humanity's continuous quest to understand randomness, risk, and uncertainty. By exploring its development, we gain insights into the evolution of mathematical thinking and its profound impact on our lives. Probability in ancient civilizations. Probability is a concept that dates back to ancient civilizations, where it emerged from the need to understand and predict uncertain events. 1. Ancient Egypt. In ancient Egypt, probability was connected to games of chance, such as dice games. The Egyptians used mathematics to calculate the odds and outcomes of these games. 2. Ancient China. Ancient Chinese scholars also made significant contributions to probability. They developed methods for calculating probabilities in games of chance and laid the groundwork for later mathematical developments. 3. Roman dice games. The Romans had their own dice games and methods of understanding probability. These games played a role in introducing probability concepts to the Western world. These early efforts were the precursors to the formal development of probability theory. The Renaissance of probability. One of the pivotal moments in the history of probability occurred during the Renaissance, thanks to the brilliant Italian mathematician and polymath, Girolamo Cardano, 1501–1576. Girolamo Cardano. Cardano was a mathematician, physician, and astrologer who made significant contributions to the field of probability. He is best known for his work, Liber de Ludo Alii, the book on games of chance published in 1564. This book is considered the foundation of probability theory. Liber de Ludo Alii. Cardano's book explored various games of chance, including dice games and card games, and introduced the concept of probability. He discussed the rules of probability, how to calculate odds, and the concept of equally likely outcomes. Cardano's work laid the groundwork for later mathematicians, such as Pascal and Fermat, to further develop probability theory. Girolamo Cardano's Liber de Ludo Alii marked the beginning of a systematic approach to understanding uncertainty, making him a key figure in the history of probability. It set the stage for the exploration of probability in a more structured and mathematical manner. The correspondence and the birth of probability theory. In the 17th century, the field of probability saw significant development through the correspondence of two remarkable mathematicians, Blaise Pascal and Pierre de Fermat. Blaise Pascal, 1623–1662. Blaise Pascal, a French mathematician, physicist, and inventor, was instrumental in the development of probability theory. In 1654, Pascal wrote a series of letters to Pierre de Fermat, which laid the foundation for the theory of probability. Pierre de Fermat, 1601–1665. Fermat, a French lawyer and mathematician, was also a key figure in the history of probability. He responded to Pascal's letters, and their correspondence addressed the problem of points, a famous probability problem related to gambling. The problem of points. The problem of points revolved around how to fairly divide the stakes in an unfinished game of chance when it was interrupted. Pascal and Fermat's correspondence led to the development of the concept of expected value and probability distributions. This collaboration between Pascal and Fermat marked a significant step in the formalization of probability theory, and their work laid the groundwork for future advancements in the field. The problem of points remains a classic example of early probability problem solving. Probability in the 18th century. The 18th century saw the continued expansion and development of probability theory, with several notable mathematicians contributing to its growth. 1. Abraham de Moivre, 1667–1754. De Moivre, a French mathematician, made significant contributions to probability and is known for the development of the normal distribution. His work laid the foundation for the study of large numbers of independent, identically distributed random variables. 2. Thomas Bayes, 1701–1761. Thomas Bayes, a British statistician and theologian, introduced Bayes' theorem, which is fundamental in probability and statistics. His theorem addressed the problem of updating probabilities when new information becomes available. 3. The development of the normal distribution. The concept of the normal distribution, also known as the Gaussian distribution, began to take shape during this period. The normal distribution is central to probability and statistics, describing the distribution of many naturally occurring phenomena. The 18th century marked a period of enlightenment in probability theory, where these mathematicians made significant strides in understanding randomness and uncertainty. Their contributions paved the way for the more formalized development of probability theory in the following centuries. A new perspective on probability. In the late 18th and early 19th centuries, the French mathematician Pierre-Simon Laplace played a pivotal role in shaping the field of probability with his classical interpretation. Pierre-Simon Laplace, 1749–1827. Laplace is often referred to as the French Newton, due to his significant contributions to mathematics, physics, and astronomy. He introduced the concept of the classical interpretation of probability in his work, A Philosophical Essay on Probabilities, published in 1814. The classical interpretation. Laplace's classical interpretation of probability emphasized a deterministic view of probability. He argued that if we had complete knowledge of the present state of the universe and all the relevant laws of nature, we could, in theory, predict all future events with certainty. Laplace's demon. Laplace's view gave rise to the concept of Laplace's demon, an imaginary entity that, if it knew the position and momentum of all particles in the universe, could predict the future and retrodict the past. Laplace's classical interpretation had a profound impact on the philosophical and scientific understanding of probability. It marked a shift from earlier views and laid the groundwork for the continued development of probability theory. Two distinct approaches to probability. Frequentist probability. In the frequentist interpretation, probability is based on the relative frequency of events observed in the long run. It views probability as an objective concept, where the probability of an event is determined by the number of times it occurs in a large number of trials. This approach is often associated with classical Bayesian probability. The Bayesian interpretation of probability is subjective, focusing on the degree of belief or uncertainty in an event. It allows for the incorporation of prior knowledge and updating probabilities as new information becomes available. Bayes' theorem is a fundamental tool in Bayesian probability, enabling the calculation of conditional probabilities. Key differences. Frequentist probability is often seen as more objective, relying on observed data, while Bayesian probability incorporates subjective beliefs and prior information. Key differences. Frequentist methods are commonly used in classical statistics, while Bayesian methods are prevalent in fields like machine learning and Bayesian inference. The debate between these two interpretations has been ongoing for centuries, and both have their strengths and limitations. The choice between them often depends on the problem at hand and the available data. Probability in the 20th century. The 20th century witnessed significant advancements in probability theory, along with the formalization of its foundations. It also marked the expansion of probability into various fields. 1. Axiomatic foundations. In the early 20th century, mathematicians like Andrei Kolmogorov established axiomatic foundations for probability theory. Kolmogorov's axioms provided a rigorous framework for the study of probability, defining probability in terms of measure theory. 2. Modern applications. Probability theory found widespread use in diverse fields, including statistics, finance, science, engineering, and information technology. The theory of stochastic processes, a branch of probability, became crucial in modeling random phenomena, leading to advances in physics, economics, and more. 3. Computational probability. The advent of computers revolutionized probability calculations. Monte Carlo simulations and computational techniques made it possible to solve complex probabilities. 4. Quantum probability. Quantum mechanics introduced a new dimension to probability with concepts like quantum probability amplitudes, essential in understanding the behavior of particles on a quantum scale. The 20th century marked a period of immense growth and diversification in the field of probability, solidifying its place in both theoretical mathematics and practical applications. Probability continues to evolve and remains at the heart of numerous modern probability theory. As we enter the 21st century, probability theory continues to evolve and adapt to the changing landscape of science, technology, and society. 1. Big data and machine learning. The explosion of data in the digital age has elevated the role of probability in machine learning and artificial intelligence. Probability is used for predictive modeling, natural language processing, and image recognition. 2. Bayesian inference. Bayesian methods have gained prominence in fields like data science, where they offer a flexible framework for updating beliefs and making decisions based on evidence. 3. Monte Carlo simulations. Probability-based Monte Carlo simulations are widely employed in various industries for solving complex problems and making informed decisions. 4. Network theory. Probability plays a role in network theory, which is essential for understanding the structure and dynamics of complex systems, including social networks and the Internet. 5. Cryptography. Probability is integral to the security of modern cryptographic systems, ensuring the confidentiality and integrity of digital communications. 6. Quantum computing. Quantum probability plays a central role in the emerging field of quantum computing, offering the potential for solving complex problems more efficiently. Modern probability theory stands at the intersection of data, technology, and innovation. Its principles are being applied in ways that were once unimaginable, driving advancements in science, engineering, and decision-making. The future promises further exploration and innovation. In conclusion, the history of probability is a captivating journey that spans millennia, reflecting humanity's quest to understand and quantify uncertainty. From its humble beginnings in ancient games of chance to its central role in modern science and technology, probability has evolved and adapted to meet the changing needs of society. Probability is not just a mathematical concept, it's a powerful tool for understanding the world and making informed decisions. Its enduring significance ensures that it will remain a cornerstone of scientific, technological, and societal.
Thank you.